I'm Professor Ed Gallier from the Fire Safety Engineering Group at the University of Greenwich, and I'm going to be giving this presentation. So before we go into that, I'll give you a little bit of background as to who FSEG are. So we're a team of about 20 full-time researchers. We're fire engineers, CFD specialists, psychologists, mathematicians, and software engineers. And our main research interests are in mathematical modeling and experimental analysis of evacuation dynamics in complex spaces, pedestrian dynamics in complex spaces, combustion, fire and smoke spread, fire suppression, and security. And our application areas include the aviation world, the built environment, maritime applications, and rail applications. And what I'm showing in these three animations, these three videos, are examples of some of our work. So we're involved in a lot of human behavior research to understand how people react and behave in all types of situations. And in the video I'm showing you here is some work we did for CP&I, looking at how people interact with security bollards during an evacuation. The second animation shows some work we've done using our evacuation modeling tool, EXODUS, buildingEXODUS. And here we're looking at the evacuation of a large high-rise office building in London. Using the evacuation model, we could identify problems with the existing evacuation procedures, and then using the model suggest ways to improve the efficiency of the evacuation so that the evacuation could take place in a shorter period of time and utilizing the exit capacity that we have in the building. The third animation is an example of our CFD model SMARTFIRE, and in this particular simulation, what we're simulating is the release of a chemical agent on a station platform. This is an underground station in London, and we're looking at the release of a chemical warfare agent on the station platform, and how the piston effect of a train as they enter and leave the station helps disperse that product throughout the station. Okay, so these are three examples of the types of work that the Fire Safety Engineering Group are involved with. We've been developing our EXODUS and SMARTFIRE tools continuously since the 1990s. We have extensive validation history of these tools, and they're used in something like 35 countries around the world. One of the key features of our modeling tools is that you can couple them. You can take the output from SMARTFIRE and couple it with the evacuation model so that you can see how the people react to the developing fire situation. The CFD code will calculate things like the smoke concentration, the visibility, toxic gas concentration, heat, radiated fluxes, and so on. And all of that's imposed on the evacuation simulation. And EXODUS takes into account of these factors through fractional effective dose models. And so we can then run the evacuation and see how the evolving situation is affecting the people during the evacuation. So we can get a really good idea of how an evacuation would unfold in the presence of a fire or other types of hazards. So that in a nutshell gives you some idea of the sort of work that we do. While I've got your attention, I just wanted to identify two other security-related developments that we've been working on. One is a version of EXODUS we call matEXODUS, and matEXODUS stands for marauding armed terrorists. So rather than having real people take the role of the terrorist, as we've just been discussing, we have a simulated environment. So it's running within the EXODUS software, the actual terrorist behavior. And in this animation, what I'm showing you is the terrorist moving around and interacting with the crowd. So this is all now a simulation. So we've built in some intelligence into the terrorist movement. He's hunting down targets and he's opening fire on the targets. The cone that you see is what we call his shooting cone. So this is the area in which he can target people. And he's hunting around for targets. And the simulated crowd is responding to the threat. So they're all trying to get away from the terrorists. And you can see he's now closing in on this group, and some of the agents will break away and try and move away from the threat. Okay, so that's matEXODUS. So it's a simulation environment we've been developing to simulate the impact of a marauding armed terrorist in a crowded place. This is with the support of the DSTL. So this is a research project with DSTL. The very last slide I want to show you is some work we've been doing on COVID-19. And here we've modified the SMARTFIRE software to simulate the release of respiratory aerosols, aerosol droplets. And here you can see a passenger train environment where we have two people, one seated by the window and one seated on the aisle, and they're infected with COVID-19, and we're looking at the respiratory droplets and how they are dispersed in the space given the ventilation. So we have the air coming in at the top and being taken out at the bottom, and being recirculated. So there's also recirculated aerosols being pumped back into the environment. But using this sort of tool, we can identify, for example, hazardous locations, the impact of physical distance, and how the droplets may spread and disperse as a result of the ventilation system. In this animation here, this is again a SMARTFIRE simulation, and here we have an infected person walking around a supermarket, and he's with each of his breaths, he's releasing aerosols containing the COVID virus, and we're looking at how this spreads through the supermarket, how the aerosol droplets spread. Okay, now this is just simply a moving source of aerosol without taking into account the wake effect caused by the moving person. In this animation at the bottom here, we've got 4 people walking in a row here and 4 people approaching, and the person in the front here is releasing infected respiratory aerosols. And we're looking at how the wake effect of the turbulent wake effect caused by the movement of the people is dispersing the droplets. Now, each of those people are 2 meters apart, but as you can see, the droplets are spreading well beyond the 2 meter distance due to the effect of the wake effect. And also these people that were approaching have also had an effect on the distribution of droplets, but in a positive sense. So they're pulling droplets away from these agents that are following the person in the lead. And this last animation here is an example of Exodus, where we've imposed physical distancing. So now the agents are trying to keep 2 meters apart. We don't force agents to keep 2 meters apart because that's very unrealistic. While people might try to keep 2 meters apart, they don't always succeed. And in this simulation, we have the agents moving through the space, attempting to maintain a 2 meter separation. And where these, each circle is a meter radius circle. So where the circles overlap, it indicates that the agents are closer than 2 meters. And within Exodus, we calculate the degree of overlap, how close they are coming to each other. We measure the duration of the close contact, and then we calculate a proximity dose. So for a given simulation, we can calculate the impact of that circulation environment, the movement through the space, and how close people have come together. So you can use this sort of simulation tool to help you manage your throughput. How can you maximize your throughput through the space? How can you maximize your occupancy while maintaining, while minimizing the proximity dose? And we also come up with a critical proximity dose, which is based on the being 2 meters apart, closer than 2 meters apart for more than 15 minutes. We can calculate a critical dose, and that again can also give you some very valuable information. Thank you very much for your time. I'll be happy to take any questions. Thank you. Please do get in touch with me. I'm Professor Ed Gallia, and you have my email address.